Read chapter Thermodynamics of Physical Chemistry from the book Physical Chemistry by R.L. Madan. Chapter 10 Thermochemistry. 10.1 Introduction. The branch of chemistry which deals with the heat changes accompanying chemical reactions is called thermochemistry. A chemical reaction involves rearrangement of atoms, that is, some bonds within the reactant molecules are broken while some new bonds in molecule of the products are formed. Energy is consumed in the dissociation of bonds while energy is evolved when the bonds are formed. If the total energy evolved is greater than the total energy consumed, then the net result is the release of energy. On the other hand, if the energy consumed is greater than the energy evolved, the net result is the absorption of energy. All chemical reactions are usually accompanied by energy changes. These energy changes appear in the form of heat, light, work, electricity, etc. These energy changes are of great practical utility, both for domestic and industrial purposes. A few reactions along with the form in which the accompanying energy changes appear and the use to which they are put are listed below. First, burning of coal in air produces heat. That's why it is used as a fuel. Carbon solid plus oxygen gas is equal to CO2 gas plus heat. Second, digestion of metabolism of carbohydrates in biological system produces heat which maintains the body temperature. Third, burning of candle, that is wax, in air produces heat and light. It is therefore used as a source of light. Wax is a hydrocarbon. 4. Reaction that takes place in galvanic cell produces electrical energy which may be used to run an electric motor or to ring a bell, etc. Zn solid plus Cu2 plus aqueous is equal to Zn plus 2 aqueous plus Cu solid. Units of heat and work. The heat changes are measured in calories, kilocalories, joules and kilojoules. 1 calorie is equal to 4.184 joule. 1 kilocalorie is equal to 4.184 kilojoule. The SI unit of heat is joule or kilojoule. Work is measured in ergs or joules. The SI unit of work is joule. 1 joule is equal to 10 raised to power 7 ergs. The SI unit of energy or work is joule, named after the physicist James Joule. The joule is a fairly small quantity of energy. It is the amount of kinetic energy possessed by a 2 kg mass moving at a speed of 1 meter per second. E is equal to half mv square is equal to half into 2 kg into 1 meter per second square, that is equal to 1 joule. 10.1.1 Enthalpy and enthalpy change. When a process is carried out at constant pressure and temperature, there is a change in volume. If the volume increases, some mechanical work is done by the system so that the internal energy decreases. Similarly, if the volume decreases, some mechanical work is done on the system so that the internal energy increases. In all such processes occurring at constant temperature, when pressure remains constant, the total energy of a system is given by a thermodynamic quantity called heat content or enthalpy of the system and not by internal energy. It is denoted by H and is defined mathematically by the equation H is equal to U plus PV, where U is the internal energy and P and V are the pressure and volume of the system respectively. The enthalpy of a system may be defined as the sum of the internal energy and the product of pressure and volume of the system. The physical significance of enthalpy may be put as under: the enthalpy of a substance is the amount of energy stored within the substance that is available for conversion into heat. Like internal energy, the heat content or enthalpy of a substance is also a state function, that is, depends only on state of the system and is independent of the manner by which the state has been attained. First, enthalpy change. Like internal energy, the absolute value of enthalpy of a substance cannot be determined. However, the change in the enthalpy when a system undergoes a change can be determined experimentally accurately, and that serves our purpose. IUPAC recommends the use of notation U in place of E for internal energy. A relation between enthalpy change and internal energy change exists as follows. Change delta H is equal to delta U plus P delta V. Delta U is equal to U2 minus U1 represents the change in the internal energy. Delta V is equal to V2 minus V1 represents the change in volume of the system. Thus, enthalpy change of a system may be defined as the sum of internal energy change and the pressure volume work done. If QP is the heat absorbed at constant pressure, then QP minus delta H. Thus, enthalpy change is the heat absorbed or evolved at constant pressure. Enthalpy change is a very useful quantity. Knowledge of this quantity is needed when we want to plan the heating or cooling required to carry out an industrial chemical reaction at constant temperature. It is also needed to compute temperature dependence of equilibrium constant. Second, standard enthalpy change. Enthalpy change is a reaction when all the reactants and the products are in their standard states, that is at 298 Kelvin, and under a pressure of 1 atmosphere is known as the standard enthalpy change. It is usually represented by delta H naught. As a chemical reaction involves breaking of bonds of the reactants and the formation of new bonds in the products, some net energy change called the enthalpy of reaction takes place. Enthalpy change of a reaction is equal to energy consumed to break the bonds of the reactants minus energy released in the formation of the bonds in the products. If energy consumed is more than energy released, the net result in the absorption of energy and the reaction is endothermic. If energy released is more than energy consumed, the net result is the evolution of energy and the reaction is exothermic. 10.2 Latest sign conventions for Q or delta H, delta U and W. First, when heat is absorbed by the system, Q is positive. When heat is given out by the system, Q is negative. When heat is absorbed by the system, delta U is positive. When heat is given out by the system, delta U is negative. When work done on the system, W is positive. When work done is done by the system, W is negative. 10.2.1 Exothermic and endothermic reactions. Exothermic reactions are those reactions which are accompanied by the evolution of heat. The quantity of heat produced is shown along with the product with a plus sign. A few examples of exothermic reactions are given below. C plus O2 is equal to CO2 plus 393.5 kJ. H2 plus half O2 is equal to H2O plus 248.8 kJ. CH4 plus 2O2 is equal to CO2 plus H2O plus 890.4 kJ. Endothermic reactions are those reactions which are accompanied by absorption of heat. Heat absorbed can be written with the products with a minus sign. A few examples of endothermic reactions are given below. N2 plus O2 is equal to 2NO minus 180.7 kJ. C plus H2O is equal to CO2 plus H2 minus 131.4 kJ. C plus 2S is equal to CS2 minus 92.0 kJ. The enthalpy change accompanying a reaction is given by delta H is equal to heat content of products minus heat content of reactants, that is HP minus HR. A reaction is exothermic if the total heat content of the reactants is more than that of the products, that is HR is more than HP. Thus, delta H will be negative for an exothermic process. Thus, the exothermic reactions given above may be written in terms of delta H as CS plus O2 is equal to CO2. Here, delta H is equal to minus 393.5 kJ. H2 is equal to half O2. Here H2 converted into H2O, where delta H is equal to minus 285.8 kJ. CH4 plus 2O2 is equal to CO2 plus 2H2O. Here delta H is equal to minus 890.4 kJ. A reaction is endothermic if the total heat content of reactants is less than that of products, that is HR is less than HP. Thus, delta H will be positive for endothermic reaction. Endothermic reaction given above may be written in terms of delta H as N2 plus O2 is equal to 2NO. Delta H is equal to plus 180.7 kJ. C plus H2O is equal to CO plus H2. Delta H is equal to plus 131.4 kJ. C plus 2S is equal to CS2. Delta H is equal to plus 92.0 kJ. Exothermic and endothermic reactions may be represented graphically as shown in the figures. 10.2.2 Thermochemical equations. A balanced chemical equation not only indicating the quantities of the different reactants and products but also indicating the amount of heat evolved or absorbed is called a thermochemical equation. Fractional coefficients are allowed in writing a thermochemical equation. For example, the formation of water is written as H2 plus half O2 is equal to H2O. Delta H is equal to minus 285.8 kJ. Thus, 285.8 kJ of heat is produced when 1 mole of hydrogen reacts with half mole of oxygen. If the quantities of reactants are doubled, the heat produced will also be doubled. For example, in the above case may be written as 2H2 plus O2 is equal to 2H2O. Delta H is equal to minus 571.6 kJ. Some important points about thermochemical equations. First, unless otherwise mentioned, delta H values are for standard state for the substance, that is at 298 Kelvin and 1 atmospheric pressure. Second, the physical state of the different substances must be mentioned as the heat evolved or absorbed depends upon the physical state of the substances. Third, if the coefficients of the substances are multiplied or divided by some number, the value of delta H is also multiplied or divided by the same number. Fourth, if the reaction is reversed, the sign of delta H changes but the magnitude remains the same. 10.3 Heat of reaction or enthalpy of reaction. The amount of heat evolved or absorbed in a chemical reaction when the number of moles of the reactants as represented by the chemical equation have completely reacted is called the heat of reaction. Let us consider the following two examples. C plus O2 is equal to CO2. Delta H is equal to minus 393.5 kJ. C plus 2S is equal to CS2. Delta H is equal to plus 92.0 kJ. The first equation indicates that when 1 mole of solid carbon combines completely with 1 mole of oxygen gas, 393.5 kJ of heat are produced. Similarly, the second equation tells that 1 mole of solid carbon reacts completely with 2 moles of sulfur. 92 kJ of heat are absorbed. Heat of reaction. Delta H is equal to heat content of products minus heat content of reactants. Delta H is equal to sum of enthalpies of product minus sum of enthalpies of reactants. If the reaction is reversed, the sign of delta H is also reversed. 10.3.1 Factors influencing heat of reaction. The heat of reaction depends upon a number of factors as explained below. First, quantities of the reactants involved. If the quantities of the reactants are changed, the heat of reaction changes proportionally. Second, physical state of the reactants and products. Since latent heat is evolved in the change of state, the physical state of the reactants and products affect the heat of reaction. For example, when hydrogen and oxygen gases combine to form liquid water, the heat of reaction is different from the value when they combine to form water vapors. H2 gas plus half O2 gas is equal to H2O liquid. Delta H is equal to minus 285.8 kJ. H2 gas plus half O2 gas is equal to H2O gas. Delta H is equal to minus 248.8 kJ. It is therefore essential to write the symbols solid, liquid, gas or aqueous to indicate whether a particular substance is solid, liquid, gas or an aqueous solution. 3. Allotropic modifications. Heat of reaction changes in a different allotropic form if involved in a reaction. For example, carbon diamond plus O2 gas is equal to CO2 gas. Delta H is equal to minus 395.4 kJ. Carbon graphite plus O2 gas is equal to CO2 gas. Delta H is equal to minus 393.5 kJ. 4. Concentration of solutions. If the solutions are involved in a reaction, their concentrations affect the heat of reaction. 5. Temperature. The heat of reaction depends upon the temperature at which the reactant and products are taken. Generally, the heat of reaction increases with temperature. 6. Conditions of constant pressure and or constant volume. This concerns whether the reaction takes place at constant pressure or at constant volume. If QP and QV represents the heat of reactions at constant pressure and volume respectively, then the following equations is applicable. QP is equal to QV plus delta NGRT, where delta Ng is equal to Np minus Nt. Nr. Np and Nr represents the number of moles of gaseous reactants and the products respectively. R and T have the usual meanings. 10.3.2 Heat or enthalpy of combustion. The heat of combustion of a substance is defined as the heat change. Usually the heat evolved when 1 mole of substance is completely burned or oxidized in oxygen. For example, C solid plus O2 gas is equal to CO2 gas. Delta H is equal to minus 393.5 kJ. When 1 mole of carbon burns completely in oxygen, 393.5 kJ of heat is evolved. Thus, heat of combustion of carbon is 393.5 kJ. The significance of the words burns completely must be clearly understood. For example, carbon may be oxidized to carbon monoxide or carbon dioxide. The heat evolved in the two cases are different, viz. C solid plus half O2 gas is equal to CO gas. Delta H is equal to minus 110.5 kJ. C solid plus O2 gas is equal to CO2 gas. Delta H is equal to minus 393.5 kJ. Complete oxidation means oxidation to CO2 and not to CO. Hence the heat of combustion of carbon is 393.5 kJ per mole. 10.3.3 Measuring the enthalpy of combustion. We use an accurate calorimeter for measuring the enthalpy of combustion. This calorimeter is called bomb calorimeter. The inner part is made of strong steel coated inside with some non-oxidizable material. A weighed amount of the substance is taken in a cup C. A platinum wire W is connected between the rod R and G. This initiates the reaction when heated electrically. Oxygen is introduced through the inlet tube T until the pressure of about 20 atmospheres is attained inside. The bomb is placed inside water in a double-jacked calorimeter. The substance is ignited by passing electric current through the wire W. Once the ignition is initiated, it continues till the whole of the substance is completely burned with the help of oxygen present. The rise in the temperature of water is noted using a Beckmann thermometer graduated to 1 divided by 100 of a degree. Also, the heat capacity of the calorimeter is obtained by burning a known mass of a substance of known enthalpy of combustion. Usually benzoic acid of high purity is taken for this purpose. It has enthalpy of combustion equal to minus 3226.7 kJ per mole. Calculations are done based on the principle that total heat lost is equal to the total heat gained. 10.3.4 For the working of a human body, we eat carbohydrates, proteins, fats, etc. in the form of food. The carbohydrates are first decomposed in our body by the enzymes to form glucose, which is then oxidized by the oxygen that we inhale to produce energy as given by the following equation. C6H12O6 solid plus 6CO2 gas is equal to 6CO2 plus 6H2O gas plus 2900 kJ. This oxidation reaction is usually called combustion of food. Different foods have different heats of combustion. These are usually expressed in terms of their calorific values. The calorific value of a fuel or food is the amount of heat in calories or joules produced from the complete combustion of 1 gram of fuel or the food. Thus, according to the above reaction, 1 mole of glucose, that is 180 gram of glucose, produces 2900 kJ of heat. Hence, the calorific values of glucose is equal to 2900 divided by 180 is equal to 16.1 kJ per gram. Calorific values of some food and fuels are given in table. For fuels, wood is equal to 16,000, charcoal 29,000, natural gas 46,000, kerosene 38,000, ghee 37.65, butter 30.50, cheese 14.56, milk 4.90, curd 2.51, soybean 18.07, fish 5.7, meat 12.0, egg 5.4, sugar 16.0, rice 16.7, potatoes 4.0. Applying chemistry to life. There is an obsession among people, particularly among women, to lose weight and look slim. Health conscious consumers of food make it a point to read book labels and to make dietary choices. People are willing to pay higher prices for packed foods that both good and are low in fat calories. Calorie contents of food is experimentally determined using the techniques of thermochemistry. A weighed sample of food is burnt in a comb calorimeter and the heat generated by combustion is determined by noting the increase in temperature. The heat generated per gram gives the energy content calorific value of the food. 10.4 Standard state. The standard molar enthalpy of every element at 1 atm pressure and 298.15 Kelvin in the most stable state is taken as 0. These conditions of 1 atm pressure and 298.15 Kelvin are called standard state conditions. It is not possible to determine the absolute value of molar enthalpy, but we can use the above convention to find out the standard molar enthalpy of a substance. The most stable form of hydrogen is gaseous H2, that of bromine is liquid Br2, while that of iodine is solid I2. Their molar standard enthalpies are taken as 0 at 1 atm pressure and 298.15 Kelvin temperature. In case of elements exhibiting allotropy, we consider the most stable form under the conditions of standard state. 10.4.1 Enthalpy of formation and standard enthalpy of formation. Heat of formation or enthalpy of formation. The enthalpy of formation of a substance is defined as the heat change that takes place when 1 mole of the substance is formed from its elements under given conditions of temperature and pressure. It is usually represented by delta HF. Standard enthalpy of formation of a substance is defined as a heat change accompanying the formation of 1 mole of the substance in the standard state from its elements, also taken in the standard state. It is usually represented by delta H naught F. For example, in the reaction C solid plus O2 gas is equal to CO2 gas. Delta H naught F is equal to minus 393.5 kJ. When 1 mole of CO2 is formed from its elements which carbon solid and oxygen gas, all substances being taken in their standard state, 393.5 kJ of heat is produced. Hence, the standard heat of formation of gaseous CO2 is 393.5 kJ per mole. Standard enthalpies of formation of some compounds are given below. Carbon solid plus oxygen gas is equal to CO2 gas minus 393.5. Carbon solid plus half O2 gas is equal to CO gas minus 110.5. H2 gas plus half O2 gas is equal to H2O liquid minus 285.9. H2 gas plus half O2 gas is equal to H2O gas minus 245.5. Half H2 plus half F2 is equal to HF gas minus 271.1. Carbon solid plus 2H2 gas is equal to CH4 gas minus 74.8. 2C solid plus 3H2 gas is equal to C2H6 gas minus 89.2. 2 carbon solid plus 2H2 gas is equal to C2H4 gas plus 52.3. 2 solid plus H2 gas is equal to C2H2 gas plus 226.8. 6 carbon solid plus 3H2 gas is equal to C6H6 liquid plus 49.0. 8 carbon solid plus 4 hydrogen gas is equal to C8H8 liquid minus 224.4. Silicon solid plus O2 gas is equal to CiO2 solid minus 910.0. S solid plus O2 gas is equal to SO2 gas minus 297.5. Na solid plus half Cl2 gas is equal to NaCl solid minus 411.0. Ca solid plus half O2 gas is equal to CaO solid minus 635.5. Half N2 gas plus 3/2 gas. Na solid plus half Cl2 gas is equal to NaCl solid minus 411.0. Ca solid plus half O2 gas is equal to CaO solid minus 635.5. Half N2 gas plus 3/2 H2 gas is equal to NH3 gas minus 46.0. N2 gas plus 2H2 gas is equal to N2H4 liquid plus 50.6. Cs plus 2H2 gas plus half O gas is equal to CH3OH liquid minus 238.9. 2C solid plus 3H2 gas plus half O2 gas is equal to C2H5OH liquid minus 277.7. 10C solid plus 4H2 gas is equal to C10H8 solid plus 60.2. 10.4.2 Importance of standard enthalpies of formation. Knowing the standard enthalpies of formation of the different compounds involved in a chemical reaction, the standard enthalpy changes of the given reaction can be obtained using the formula delta H naught reaction is equal to sum of standard heats of formation of product minus sum of standard heats of formation of reactants. That is, delta H naught reaction is equal to sum of delta H naught F products minus summation of delta H naught F of reactants. Thus, for a general reaction, A plus B plus C is equal to CC plus DD. Delta H naught reaction is equal to C delta H naught FC plus D delta H naught FD minus A delta H naught FA plus B delta H naught FB. Remember, delta H naught F is taken as 0 for the elements in a reaction. Suppose we are interested in finding the heat of combustion of methane. The reaction is represented as CH4 gas plus 2O2 gas is equal to CO2 gas plus 2H2O liquid. The heat of delta H naught reaction is equal to delta H naught F for CO2 plus 2 into delta H naught F for H2O minus delta H naught for CH4 plus 2 into delta naught F for O2. Putting the values of heat of formation in the standard state. Delta H naught reaction is equal to minus 393.5 plus 2 into minus 285.8 minus bracket minus 74.9 plus 0 is equal to minus 965.1 plus 74.9 is equal to minus 890.2 kilojoules. Delta 10.4.3 Enthalpy or heat of neutralization. The heat of neutralization of an acid by a base is defined as the heat change when 1 gram equivalent of the solid is neutralized by a base. The reaction being carried out in dilute aqueous solution. The heat of neutralization of a base by an acid is defined in a similar manner. For example, when 1 gram equivalent of HCl is neutralized by NaOH or 1 gram equivalent of NaOH is neutralized by HCl in dilute or aqueous solution, 57.1 kJ of heat is produced. NaOH plus HCl is equal to NaCl plus H2O. Delta H is equal to minus 57.1 kJ. Hence, the heat of neutralization of HCl with NaOH or NaOH with HCl is 57.1 kJ. The heat of neutralization of any strong acid HCl, HNO3, H2SO4 with a strong base NaOH, KOH or vice versa is always the same, that is 57.1 kJ. This is because the strong acids, strong base and the salts that they form are all completely ionized in dilute aqueous solution. Thus, the reaction between a strong acid and a strong base may be written as Na positive plus OH negative plus H positive plus Cl negative is equal to Na positive plus Cl negative plus H2O. Delta H is equal to minus 57.1 kJ. Cancelling out common ions on the two sides, we have H positive aqueous plus OH negative aqueous is equal to H2O liquid. Delta H is equal to minus 57.1 kJ. Thus, neutralization may be regarded as a reaction between the H positive ions given by the acid with the OH negative ions given by the base. Since strong acid and strong base ionize completely in a dilute aqueous solution, the number of H positive ions and OH negative ions produced by 1 gram equivalent of the strong acid and the strong base is always the same. Hence, the heat of neutralization between a strong acid and a strong base is always the same, that is minus 57.1 kJ. Compared to a strong acid, a weak acid produces a smaller number of H positive, hence the heat of neutralization is smaller. Different kinds of heat or enthalpy of reaction. First, heat of solution or enthalpy of solution. The heat of solution of a substance in a particular solvent is defined as the heat change, that is the amount of heat evolved or absorbed when 1 mole of the substance is dissolved in such a large volume of the solvent that further addition of the solvent does not produce any more heat change. Thus, the thermochemical equations for the dissolution of KCl and CuSO4 in water may be represented as KCl solid plus aqueous is equal to KCl aqueous. Delta H is equal to plus 18.6 kilojoule. CuSO4 solid plus aqueous is equal to CuSO4 aqueous, that is delta H is equal to minus 66.5 kilojoule. Thus, the heat of solution of KCl is equal to plus 18.6 kilojoule per mole, and the heat of solution of CuSO4 is equal to minus 66.5 kilojoule per mole. It is interesting to note that the salts like copper sulfate, calcium chloride, etc., when present in the hydrated state, that is CuSO4.5H2O, CaCl2.6H2O, etc., dissolves with the absorption of heat. For example, CuSO4.5H2O plus aqueous is equal to CuSO4 aqueous. Delta H is equal to plus 11.7 kilojoule. Thus, it can be generalized that the process of dissolution is usually endothermic for A. Salt which do not form hydrates like NaCl, KCl, KNO3, etc. B. Hydrated salts like CuSO4.5H2O, CaCl.6H2O, etc. Second, heat or enthalpy of hydration. The amount of heat change, that is the heat evolved or absorbed when 1 mole of the anhydrous salt combines with the required number of moles of water so as to change into a hydrated salt, is called the heat of hydration. For example, the heat of hydration of copper sulfate is minus 78.2 kilojoule per mole. This is represented as follows. CuSO4 solid plus 5H2O is equal to CuSO4.5H2O solid. Delta H is equal to minus 78.2 kilojoule. In fact, both the cations and anions get hydrated separately to give the hydrated salt. Third, lattice energy. It would be interesting to link enthalpy of solution and enthalpy of hydration with lattice enthalpy. Lattice enthalpy of an ionic compound is the enthalpy change which occurs when 1 mole of an ionic compound dissociates into its ions in the gaseous state. For example, for NaCl, we have Na positive Cl negative solid is equal to Na positive gas and Cl negative gas. Delta H naught lattice is equal to plus 788 kilojoule per mole. The connection between the lattice enthalpy, enthalpy of solution and enthalpy of hydration can be understood by taking the example of an ionic solid AB as under, where delta H naught stands for standard enthalpy change for different processes under standard conditions of temperature and pressure, respectively. Thus, if we know two of the three quantities, delta H of solution, delta H naught lattice, and delta H naught hydration, the third can be calculated. We can also write the following equation as per Hess law. Delta H naught of solution is equal to delta H naught of lattice plus delta H naught of hydration. For most ionic compounds, delta H naught of solution is positively and the dissolution process is endothermic. Therefore, as per Le-Chatelier's principle, the solubility increases with the rise in temperature. If the lattice energy is very high, the dissolution may not take place at all. We must remember that energy is required to break away ions from the lattice positions, while energy is evolved when hydration of ions take place. In general, we can say if delta H naught hydration is more than delta H naught lattice, dissolution will take place. If delta H naught hydration is less than delta H naught lattice, dissolution will not take place. 4. Heat or enthalpy of fusion. Heat of fusion is the heat change that takes place when 1 mole of the solid substance changes into its liquid state and its melting point heat of fusion, that is delta H fuse, of ice. It may be represented as follows. H2O solid is equal to H2O liquid. Delta H is equal to plus 6 kilojoule. 5. Heat of vaporization. It is the heat change that takes place when 1 mole of liquid changes into its gaseous state at its boiling point. For example, the heat of vaporization, that is delta H vapor of water into gaseous state at the boiling point, is 40.7 kilojoule. It may be represented as follows. H2O solid is equal to H2O liquid. Delta H is equal to plus 6 kilojoule. 6th, heat of sublimation. Heat of sublimation of a substance is the heat change that takes place when 1 mole of the solid changes directly into vapor phase at a given temperature below its melting point. Sublimation is the process in which a solid on heating changes directly into gaseous state below its melting point. For example, the heat of sublimation of iodine is 62.39 kJ per mole. It is represented as follows. I2 solid is equal to I2 gas. Delta H is equal to 63.39 kJ. Most solids that sublime readily are molecular solids, that is iodine and naphthalene, etc. 10.6 Hess law of constant heat summation. G.H. Hess, a Russian chemist, in 1840 gave a law about the heats of reaction which is stated as follows. The total amount of heat evolved or absorbed in a reaction is the same whether the reaction takes place in one step or in number of steps. In other words, the total amount of heat changes in a reaction depends only upon the nature of the initial reactant and the nature of the final products, and not upon the path or the manner by which this change is brought about. An analogy for Hess law can be made to the floors in a building. Suppose you take the lift from the ground floor to the 10th floor of the building. The net gain in your gravitational potential energy is the same whether you go directly there or move out at each floor on your way up. Hess law may be illustrated with the help of the following examples. First, sulfur rhombic burns to form SO3 to evolve 395.4 kJ of heat. Sr plus 3 by 2 O2 gas is equal to SO3 gas. Delta H is equal to minus 395.4 kJ. Sulfur may changes to SO3 in two steps as given below. Sr plus O2 gas is equal to SO2 gas. Delta H is equal to minus 297.5 kJ. SO2 gas plus half O2 gas is equal to SO3 gas. Delta H is equal to minus 97.9 kJ. Total heat evolved in two steps is minus 297.5 plus minus 97.9, that is minus 395.4 kJ. This is the same as for the direct reaction in one step. Second, when carbon granite burns to form carbon dioxide directly in one step, 393.5 kJ per mole of heat is evolved. C solid plus O2 gas is equal to CO2 gas. Delta H is equal to minus 395.5 kJ. If carbon burns to form carbon monoxide first, which then burns to form carbon dioxide, the heat evolved in the two steps are as follows. C solid plus half O2 gas is equal to CO gas. Delta H is equal to minus 111.5 kJ. Carbon monoxide gas plus half O2 gas is equal to CO2 gas. Delta H is equal to minus 282.0 kJ. Thus, the total heat evolved in two steps comes out to be minus 111.5 plus minus 282.0, that is minus 393.5 kJ, which is the same when the reaction takes place directly in one step. Proof of Hess law considers a general reactions. A is converted into D. Suppose the heat evolved in this reaction directly is Q joules. Now suppose the same reaction takes place in three steps as follows. A is converted into B, is converted into C, is converted into D. Suppose the heat evolved in these steps are Q1, Q2 and Q3 joules respectively. Thus, the total heat evolved from A to D is equal to Q1 plus Q2 plus Q3 is equal to Q0 joules. Say, according to the Hess law, we must have Q is equal to Q0. Suppose Hess law is not correct. In the case, either Q0 is less than Q or Q0 is more than Q. Let us suppose Q0 is more than Q. We shall now complete the cycle, that is, we shall go from A to D through three steps and return to A in one step. And we shall see that the heat change takes place. In heat change from A to D, Q joules of heat are evolved. Therefore, in direct process from D to A, Q joules of heat are absorbed. Now, if we move from A to D in step and returns to A directly, Q dash minus Q joules of heat is produced. Thus, by repeating the cyclic process a number of times, a large amount of heat can be created. This is, however, against the law of conservation of energy. Hence, Q0 cannot be greater than Q. Similarly, Q0 cannot be less than Q. It has to be equal to Q. Thus, Hess law is proved. 10.6.1 Applications of Hess law. Hess law is very useful in determining the heat or enthalpies of many reactions, which cannot otherwise be measured by direct methods. The thermochemical equations are added, subtracted, multiplied or divided just like other algebraic equations. Some important applications of Hess law are as follows. First, Determination of enthalpy of formation. The heat of formation of some compounds cannot be determined directly by experiments. This can be calculated by the application of Hess law. Suppose we want to determine the heat of formation of CO. C plus half O2 is equal to CO. By direct experiment it is not possible because in the reaction between carbon and oxygen we may get a mixture of carbon monoxide and carbon dioxide, but we require only carbon monoxide. Therefore from the experiment it is not possible to determine the heat of formation. We know experimentally the heat of combustion of pure carbon and carbon monoxide. It is represented by the following equation. A. C plus O2 is equal to CO2. Delta H is equal to minus 393.5 kilojoule. B. CO plus half O2 is equal to CO2. Delta H is equal to minus 283.0 kilojoule. Now applying Hess law on A and B, we get the required equation for the heat of formation of CO. This can be achieved by subtracting B from A, that is by carrying out A minus B. C plus half O2 is equal to CO2. Delta H is equal to minus 110.5 kilojoule. Therefore, enthalpy of formation of CO is equal to minus 110.5 kilojoule. Second, determination of heat of transition. Transition of an element from one allotropic form to another is a slow process that requires heating of one allotropic form of the element for a long time at constant temperature. Hence, enthalpies of transition of elements cannot be determined experimentally. They are, however, determined indirectly by means of Hess law. Thus, Hess law is useful in determining the enthalpies of transition of an allotropic form such as rhombic sulfur to monoclinic sulfur, yellow phosphorus and red phosphorus, graphite to diamond, etc. Suppose we want to determine the enthalpy of transition of sulfur into sulfur monoclinic. Each variety is combustioned and heats of combustion are found out. This is represented by the following equations. A. Sr plus O2 is equal to SO2. Delta H is equal to minus 295.1 kilojoule. B. Sm plus O2 is equal to SO2. Delta H is equal to minus 296.4 kilojoule. Subtracting B from A, we get Sr is equal to Sm. Delta H is equal to minus 295.1 minus 296.5 is equal to plus 1.3 kilojoule. Thus, transition of 1 gram of atom of rhombic sulfur to monoclinic sulfur absorbs 1.3 kilojoules of heat. 3. Calculation of enthalpies from the given data. Thermochemical equations can be added, subtracted, multiplied or divided by a numerical factor like algebraic equations. Hess law is thus used for the calculation of enthalpy changes for the reactions for which direct experiment measurements are not available. Bond enthalpy or bond energy. The bond energy of a particular bond is defined as the average amount of energy released when 1 mole of the bonds are formed from isolated gaseous atom, or the amount of energy required when 1 mole of bonds are broken so as to get the separated gaseous atoms. For diatomic molecules like H2, HCl, etc., the bond energy is equal to the dissociation energy of the molecules. But for the polyatomic molecules like CH4, the bond dissociation energies of the 4 CH bonds are different. Hence, an average value is taken. Bond energies of some common bonds are given. HH 436 kilojoule per mole, HF 565, HCl 431, HBr 364, HI 297, FF 155, Cl 242, Br 190, II 149, OO 138, N double bond N 941, etc. Heat of reactions can be calculated from bond energy data. The following formula can be used directly in these calculations. Delta H reaction is equal to summation of bond energies of reactants minus summation of bond energies of product. Remember that this relationship is approximate and is valid when all substances, reactants and products in a reaction are in gaseous state. 10.7.1 Applications of bond dissociation energies. First, determination of enthalpies of reactions. This may be illustrated by taking the example of hydrogenation of ethene to ethane. CH2 double bond CH2 plus H2 is equal to CH3 CH3. In this reaction, 4 CH bonds remain intact. A double bond of in ethane is broken and HH bond is broken. On the particular side of product, 1 cc carbon bond of 2 CH bonds are formed. Thus, delta H is equal to minus delta H Cc minus 2 delta H CH plus delta H C double bond C plus delta H HH. Substituting the values of the bond energies, we got minus 120 kilojoule. Second, determination of enthalpies of formation of compounds. Consider the formation of acetone from CH and O. 3C gas plus 6H gas plus O gas is equal to CH3 C double bond O CH3. This involves the breaking of 3 HH and half OO bonds and sublimation of 3 carbons to give 6 atoms of H gas, 1 atom of oxygen gas and 3 atoms of C gas respectively. Enthalpy of sublimation of C is 720 kilojoule. It also involves the formation of 2 carbon-carbon bonds, 6 CH bonds and 1 C double bond O bond. Thus, the enthalpy of formation is given by delta HF is equal to 3 delta H HH bond plus half delta H of OO bond plus 3 delta H of C solid to C carbon minus 2 delta H of CC bond plus 6 delta H of CH bond plus delta H of C double bond O bond. Substituting the values, we got delta HF is equal to minus 348 kilojoule. 3. Determination of resonance energy. It is if a compound exhibits resonance, there is a considerable difference between the experimental and calculated values of enthalpies of formation of the compound. The difference gives the values of resonance energy. Consider the dissociation of benzene. C6H6 gas is equal to 6C gas plus 6H gas. Assuming that the benzene molecule consists of 3 CC and 3 C double bond C bonds and 6 CH bonds, the dissociation energy is calculated as delta H dissociation is equal to 3 into delta H carbon-carbon bond plus 3 into delta H of carbon double bond carbon plus 6 delta H of CH bond, which come out to be 5382 kilojoule per mole. Experiment values is known to be 5535 kilojoule per mole. This means the compound is more stable than the Kekulé structure by the amount 5535 minus 5382 is equal to 153 kilojoule per mole. This is the value of resonance energy. Resonance energy comes into play because of the resonating structures. (10.8) Variation of heat of reaction with temperature, that is Kirchhoff's equation. Heat evolved or absorbed depends upon the temperature at which the reaction is carried out. The relationship showing the variation of the heat of reaction with temperature was given by Kirchhoff in 1856. The change in the heat of reaction at constant pressure for every degree change of temperature is equal to the change in the heat capacity at constant pressure accompanying the reaction. It can be derived as under. Consider a general equation. A is converted into B. As shown in the figure, from A at temperature T1, we can reach B at temperature T2 by two different paths. Path 1, we perform the reaction at temperature T1 to obtain B at the same temperature and then heat this up to the temperature T2. Then, heat evolved in the first stage is equal to delta H1. Heat absorbed in the second stage is equal to CPB T2 to T1. When CPB is the average molar heat capacity of the products, net heat evolved is equal to delta H1 minus CPN, that is T2 to T1. Path 2. We first heat up the reactants to the temperature T2 and then perform the reaction to give the products at the same temperature. Then, if CPA is the average molar heat capacity of the reactants A, heat absorbed in the first stage is equal to CPA T2 to T1. Heat evolved in the second stage is equal to delta H2. Net heat evolved is equal to delta H2 to CPA T2 to T1. Since the initial and the final stages are the same in both of the above cases, therefore, by the law of conservation of energy, we must have net heat evolved by path 1 is equal to net heat evolved by path 2. That is, delta H1 minus CPB T2 minus T1 is equal to delta H2 minus CPA T2 minus T1, or delta H2 minus delta H1 divided by T2 minus T1 is equal to delta Cp. When the reaction is carried out at constant volume, we have the thermodynamic reaction delta H is equal to delta U plus P delta V. Under conditions at constant volume, delta V is equal to 0, delta H is equal to delta U. Hence, equation derived above takes to form delta U2 minus delta U1 divided by T2 minus T1 is equal to delta CV, where delta CV is equal to CVB minus CVA is the change in the heat capacity at constant volume. Accompanying the reaction, CVA and CVB are the mean molar heat capacities at constant volume of the reactant and the product respectively. Delta E1 and delta E2 are the internal energy changes, that is, heat of the reaction at constant volume when the reaction is carried out at temperature T1 and T2 respectively. Hence, Kirchhoff's equation may also be expressed as the change in the heat of reaction at constant volume for every degree change in temperature is equal to the change in the heat capacity of at constant volume accompanying the reaction. Summary. First, thermodynamic is the branch of chemistry which deals with heat changes accompanying chemical equations. Second, enthalpy of a system may be defined as the sum of internal energy and the products of pressure and volume of the system. Enthalpy may also be defined as the energy stored within the substance that is available for conversion into heat. Third, enthalpy change is a system may be defined as the sum of internal energy changes and the pressure volume work done. In other words, enthalpy changes is the heat evolved or absorbed at constant pressure. Fourth, if the heat is evolved in a reaction, it is exothermic. If the heat is absorbed in a reaction, it is endothermic reaction. 5. A balance equation indicating the amount of heat evolved or absorbed is called thermochemical equation. 6. The amount of heat evolved or absorbed in a chemical reaction when the number of moles of the reactants as represented by the chemical equation have completely reacted is called the heat of reaction. 7. The heat of combustion of a substance is defined as the heat change when 1 mole of the substance is completely burnt or oxidized. 8. The calorific value of a fuel or food is the amount of heat in calories or joules produced from the complete combustion of 1 gram of the fuel or the food. 9. The conditions of 1 atm pressure and 298.15 Kelvin are called standard state. 10. The standard enthalpy of formation of a substance is defined as the heat change that takes place when 1 mole of the substance is formed from its elements in the standard state, that is 298 Kelvin and 1 atm pressure. 11. Heat of neutralization of an acid by a base is defined as the heat change when 1 gram equivalent of the acid is neutralized by the base, the reaction being carried out in dilute solution. 12. Hess law. The total amount of heat evolved or absorbed in a reaction is the same whether the reaction takes place in one step or in number of steps. 13. The bond energy of a particular bond is defined as the average amount of the energy released when 1 mole of the bonds are formed from isolated gaseous atom, or the amount of energy required when 1 mole of the bonds are broken so as to get separate gaseous atoms. 14. Kirchhoff's law. The change of the heat of reaction at constant pressure for every degree change of temperature is equal to the change in the heat capacity at constant pressure accompanying the reaction. Thank you.